Hello everybody. Thanks for coming to the workshop. Today I'm going to talk about AutoGluon Tabular. This is about automatic machine learning for tabular data. You can check out the library at autogluon.mxnet.io, and if you want to help out, join us on the Slack channel AutoGluon. Obviously, I'm not the one who did the actual work. The actual work was done by those 8 gentlemen: Nick, Jonas, Alex, Hang, Pedro, Mu, Rasul, and Pratik, and I'm just here giving the talk. Let's start with something very simple, namely how to find the best food. Okay. Well, let's say I want to find the best food, and one option is, well, I could just pick maybe eggs. Eggs are tasty, right? But maybe somebody else says, well, actually bacon is much tastier than eggs, so they prefer bacon. And somebody else says, yeah, but you should be eating vegetables, and if you have a really extravagant taste, maybe you like some fish roe. So what's to be done in this case? Well, you could actually use a genetic algorithm and try to figure out which food is the best. So you basically prepare some food, see how the guest responds, says, this bacon is tasty today, and then you optimize over this further, and you might actually end up with bacon. As a matter of fact, you might not end up with this bacon, but, well, maybe fried bacon is even better than bacon, right? More cholesterol, right? So, okay, maybe not everybody's a fan of genetic algorithms. Well, you could do that with reinforcement learning. So you basically, have a state. The agent then goes and decides upon an action, such as, well, let's serve egg today. And then the environment responds and says, this egg is good. And then maybe you can improve, and you can pick both, which dish to pick, but also, how to prepare it. So maybe RL ends up with eggs. And as a matter of fact, maybe there's an improvement of this delicious egg into sunny side up. Okay. This feels kind of weird. And with food, nobody would do this, right? So there has to be a better solution. And as a matter of fact, there is one, which is simply, well, you serve the entire dish altogether. And if you paid attention to the previous slides, you would have noticed that these were actually snippets of this delicious dish that I had a year ago. So, okay, that's great. Can we do better? Right. And of course you can, because rather than just having a single course, you could have those 3 courses, and they're all delicious. And so basically you end up with a sequence of combinations of dishes. Okay. So by now, I think some of you might question my sanity, because this is a talk about machine learning and I just keep on rambling on about food. Okay, so let's go about finding the best machine learning algorithm. Well, you could go and maybe pick decision trees. After all, they're quite robust and resilient and easy to implement and fast and all of that. So trees are good. But maybe boosted trees or banked trees are even better, or random forests, right? Okay. Or maybe you're partial to neural networks. And so what you could do is you could then use a genetic algorithm to figure out that actually maybe the best thing that you should be doing is to pick a neural network. And as a matter of fact, there's a paper from last year called AmoebaNet, where the network architecture was then chosen by a genetic algorithm to find the best network architecture to solve a problem. So what I'm telling you here isn't entirely made up. This is actually something that people are concerned about in their daily research at the moment. But maybe genetic algorithms aren't your thing, so you can use reinforcement learning. And again, well, what you do is you go and, design a network architecture. You then go and, offer this up to, the system, and you see how it responds. And so maybe you end up with this multi-layer perceptron. Or maybe your reinforcement learning algorithm is able to come up with something even better. As a matter of fact, there's a paper by Zopf and Lee from 2017, which does exactly that. Now, okay, you might wonder, what does this have to do with finding the best machine learning algorithm? Well, it turns out that all the other popular machine learning toolkits also aim to find the best single model, like AutoScikit-learn, H2O, Tpot, GCP, AutoML, Autopilot, AutoWaker. They all do this. And so you might ask, well, is there a better solution? And as a matter of fact, if you look around on Kaggle, you'll see that there is, because people there actually combine a diverse variety of networks and trees and forests and nearest neighbors, and that turns out to work really well. So at that point, well, you can ask, well, can we do even better? And as a matter of fact, you can. Namely, you can use the output of one set of models as the input for the new level, and you keep on working your way through. So this way you get a very high quality output. So the one thing that I hope you noticed is that I now showed you the same set of slides twice. Once with dishes, once with machine learning algorithms, but the entire structure was the same. So the take-home message, if you remember nothing else, is that diversity is better than just finding the single best item, and also to layer a sequence of combinations is better than just one combination. Okay, so now after 6 minutes we get to the outline of this talk, namely, well, how to build what I believe is a modern AutoML system. You need to take preprocessing seriously. You need to take it seriously how to ensemble. So hyperparameter optimization per se, I feel, is overhyped in the sense that there are other ways that may get you a better answer more easily. Furthermore, stacking is a really good idea, and I'll talk a little bit about the issues that you need to worry about. And in the end, well, once you've built this, you end up with a Rube Goldberg machine, right? So in other words, you have, this bizarre chimera of multiple different architectures and networks and nearest neighbors and software packages and so on. And this gets very slow. And so you could do very hard engineering work to fix it, or you can just go and fix it with math. And we did the latter. Now, before I dive into it, have a look at the 3 lines at the bottom. This is all you really need to know to get started with AutoGluon. You need 3 lines of code. You need to import the library, you call the fit function, and then you predict. You don't even need to specify which estimation problem you're solving. We detect that automatically. Now, of course, if you want to specify it, everything can be overridden and specified, but if you don't, well, go for it. So how does one typically design an AutoML system? Well, I took this picture from Yao et al. From 2019, which is a review paper on AutoML. And so in their view, basically they start with a problem definition, and then there's some data, then you perform feature processing and model selection, and you optimize over the network, and then in the end you evaluate it, and maybe you have some loop in this case, then in the end you go and deploy. And so the question is, how can you efficiently do this? And they show a number of paths, but I believe you can actually fuse the 4th and 5th step in this case, namely the parameter optimization and the model optimization, and just, rather than finding, that single best snowflake, actually you just take an entire snowball of maybe pretty unremarkable snowflakes. So, okay, well, given that I'm showing you this picture, well, I haven't talked about feature preprocessing yet. The key point here is really you want to auto-detect everything, right? You want to auto-detect time, date, location, categorical, real values, user IDs, and so on. And this way, you can get rid of a lot of the tedious, busy work that, the user has to do, but actually that many AutoML systems don't really support very well. Now, this is great, but you shouldn't force the user, because in some cases they have actually much better prior knowledge. And so what we do is we make everything automatic, but we let the user switch it off and override it. So for instance, which embeddings to use, you might want to auto detect languages. There are a lot of things that you can do fairly easily automatically. Okay, so now what are we using as the ingredients of this approach? Well, of course, you need to have trees, and we actually use extremely randomized trees. It's one of the sklearn packages. You could probably get something similar from CatBoost and others, but we have some trees. Then we take some forests and gradient boosting, and so we take LightGBM and CatBoost and random forests from sklearn, and we pick all three of them because they perform slightly differently, and actually that diversity improves performance. And then we take a nearest neighbor classifier, and so that's more like the type of machine learning algorithms that you would have picked in the previous decade. But of course, since this is, the 2020s, well, you also use deep networks, and we basically use a best practices collection for deep networks. Namely, we go and embed, we take categorical objects where we pick explicit embeddings for text and images. You can do that too. We use residual networks when we layer the stacks on top. So this way you parameterize not around the zero function, but around the identity function. This has much better capacity control properties. We use dropout and batch norm. And of course you go multi-layer because, well, why would you not? And so this gives you a pretty solid deep network. And then in the end, well, once you've trained those individual terms, well, you check on the validation set, you optimize the weights of the components. And, well, once you do this, you end up with some combination like f of x is sum over alpha I fi of x, where the fi's are the individual baselearners. And of course, you want to make sure that they all sum up to 1. Okay, so there's your ensemble. Now, once you do this and you start wondering about things, actually, there's still a fair amount of inefficiency. So if you think about it, the validation set isn't really used for training. We just use this validation set to, pick some default parameters and do some reasonable things. So if we have, let's say, a 5-fold cross-validation, then, well, we're basically leaving out 20% of the data. Now, 20% doesn't seem like a lot, but once you actually want to go and deploy this, well, okay, throwing away 20% of the data that might have been really expensive to gather isn't really worth it. So, what to do? Well, actually, if you think about it, right, and it's basically that, different partitions really give you different outcomes. So depending on, which part I take as a training and validation set, I get a slightly different function fv out of it. I'm just indexing v by the validation set that I'm not training on. And so in this case, I have, on this picture here, 4 different functions fv. And each of them, depends on slightly different data. And of course, it, leads to slightly different outcomes. So what would you do? Well, of course, you could train on the larger dataset, but that doesn't really help you for some other reasons, because now the outputs depend on the inputs. Well, what you can do is they depend on the inputs of the training set. What you can do instead is you go and average over all the partitions. One of the nice things is that it's, in this case, okay to oversample. Okay, so what do I mean by that? Let's say we have, k equals 5, so I have 5-fold cross-validation. What I could do is I could generate 20 random partitions of the data where I'm making an 80-20 split. So each observation typically will be in the order of, 4 such FVs where it's only in the validation set. And so what I would do is I could just then go and average over those numbers for the purpose of the next layer. Well, why is this a good idea? Because in this case, I will get a more concentrated, more reliable estimate of what the score will be as the output for that bagging stage. Okay. To put this a little bit more explicitly, let's say I have the complete data, and well, we have 5 folds here, so I go and split it up into 5 splits between training and validation. And of course, on the validation set, I will just use all the training data bar the validation set and use it for the prediction there. And what's important to keep in mind is that the estimate on that validation set is now conditionally independent of the training labels. It's going to be quite important later, because when we then stack things, you really need that independence. Right. Now at test time, we just take all the predictions, we average them, and that's our consensus prediction. So in short, on the validation set, you average overestimators that aren't included in the generation, and in general, you just average over the estimators. Okay. Now let's look at stacks. Right. So this is a food-themed talk, so of course we have the unhealthy superburger here. Let's just stack one level after the other. So in the first phase, well, we go and train maybe 5 or 6 different, maybe 10 different models. And if we want to include the outputs of those models as the inputs for the next iteration, we need to make sure that those outputs don't depend on the training labels for that corresponding input. Now, if I happen to train on that particular input, well, I would be in trouble. So this is exactly where that validation split comes in very handy, because now you can go and use the predictions that were made without knowing the labels on that particular subset for the corresponding features. Okay, and so what you have is, you start with input features xi in the first layer. What you then get is, xi1 is basically the concatenation of xi and fj of xi. Right, so this is more features. Second layer, I then go and combine the previous and this one, and I keep on doing this. So if this looks familiar, it is because we just use the same strategy as what you have in a ResNet or in a DenseNet. So you can think of this as a stage-wise training of a 3-layer DenseNet, right? And it actually works quite well. The only thing is that the way how we train the individual layers is kind of weird if I were wearing my neural networks hat. So this sounds all very crazy, and well, so does it work? And as we all know, the proof of the pudding is in eating it. So let's look at Kaggle. So what we did is we picked some Kaggle datasets, and the ones that we did pick were those that the GCP, so the Google Cloud Platform AutoML system, picked as their reference datasets to illustrate what they're capable of. And then we also picked the 10 most recent meaningful datasets. And with meaningful, I mean datasets that didn't have any massive covariate shift, that were in time series, because we currently don't auto-detect time series, nor does any of the other tools for that matter. But we figured that we wanted to have something where the training data is IID, where you don't need to do any non-trivial joins of multiple tables to generate your features. Basically something where you could safely say, okay, well, these are the features, go forth and run. And what you're seeing here is that, and on Kaggle, I mean, the one thing you might want to do is you might want to compare not to the absolute value, where we do very well too, but you might want to compare how well you do relative to humans. This is basically the easiest way to evaluate your system as to, can it beat humans? How many humans can it, how much better is it, or how much worse? Because on Kaggle, you get this entire distribution of scores. And so what we did is we went and basically scraped the score distribution for each of those problems. We ran those algorithms as of, state of the art, January 2020, and we looked at where they fall. And you want to be as far on the left as possible. So what turns out to be the case is that for 2 of the datasets, we're in the 99th percentile rank. In other words, 99% of all submitted solutions are worse than what we do out of the box. In quite a few cases, we're nicely at the median. In other words, the average, well, the median engineer is probably not going to do much better than we do. The one thing to keep in mind, since this is Kaggle, usually once somebody goes and finds a nice way how to solve a problem, well, they post this kernel and then everybody else, piles in and, improves on it. So the fact that we are out of the box at that score without any of this iterative improvement that you get by the hive mind of Kaggle users is, well, quite a nice thing. So we actually tested it on our own engineers in Amazon, and we basically took a batch of novice machine learning engineers, well, or they weren't machine learning engineers before, and we trained them. And then we told them, okay, here's some problems. Can you go and beat AutoGluon? And it turns out that they couldn't. And well, you can draw a couple of conclusions from that, either that AutoGluon is so amazing, or that we did a horrible job at training the engineers, or that the engineers were just really horrible to begin with. I don't know what it is, but at least we figured that it's a worthy opponent when you're teaching machine learning. So, okay, well, fine, let's just actually look at this more numerically. And it turns out that we do very well compared to everybody else. More importantly, it turns out that if you were to pick just AutoGluon, then you would still do better than the best in hindsight combination of all the other things that we compared to, namely H2O, Tpod, GCP tables, AutoSKLearn, and AutoWeka. So that's very nice. Let's look at the details. So we normalized our performance to 1, and then we just looked at relative performance. And basically, we do well if all the other symbols are to the right of that black line, and we do less well if they're to the left. And since this is loss, absolute numbers are utterly meaningless, because let's say I have 99% accuracy, like what's the case on MNIST, then a 0.5% improvement is something that will probably get you a NIPS oral. On the other hand, if I'm performing at 60% accuracy, then improving that to 60.5 usually is not such a big deal. So therefore, absolute percentages are utterly meaningless. Relative improvements matter more. So then the next thing is, well, because you need to predetermine, some time, how long it can run. And what we did is we compared how AutoGluon and other AutoML systems improve if they're given more time. Ideally, what you want to have is that an AutoML system that's given more time performs better, right? Because, I'm paying more compute, so it better do something better. And so again, we compare it to GCP tables, H2 AutoML, AutoSKLearn, Tpod, and AutoWeka. And well, what you want is that the first column, which indicates that the system actually performs worse after 4 hours than what it performed after 1 hour, that number is small. It turns out that for some of those systems, that number is actually pretty bad. In case you wonder why those numbers don't always sum up to, 38, well, that's because a lot of other AutoML systems failed, right? So this is another thing. AutoGluon is super robust. It doesn't fail easily. That has a lot to do with how we bag and combine. And well, there's not enough time in this talk, but maybe we can take care of that in the discussion. What you do not want is, as said, that the first column has large numbers. The last column is basically where after 4 hours it's just as good or bad as before, and I think we do pretty okay there. So in most cases, more time helps. Now, well, the various tricks that I mentioned in there, AutoGluon, basically, if you don't, repeat the bagging, if you don't stack, if you don't well, hyperparameter optimization didn't actually make much of a difference. If you don't bag, if you don't use a neural network, all of those things make it worse. And so what I'm basically showing here is the average loss, and then the corresponding loss if you increase it, and the rank, ranked if I have, a number of different estimators, and we basically pick the, the other systems plus various flavors of AutoGluon, and then we look at where this falls. And yeah, basically an average rank of 2 isn't too bad. Now, the one thing that you should be worried about by now is, well, if you actually run this thing, you get a Rube-Goldberg machine. So to keep in mind, so if you have, stacking and bagging and everything, you have often multiple versions of the same model, you have multiple models, you have them in different layers. So at the end of the day, you end up with something that's fairly complex. So if you really run it until you get very, very high precision or many models and so on, then, this can be up to, 4 orders of magnitude slower than just a single model. So this is awful. So we looked at this problem because, our engineers want to have fast models, and we thought, well, maybe we can go and fix it with engineering, right? We can go and, replace the k-nearest neighbor implementation with one that's super fast, and we squeeze something out and we pick, a better tree, and we keep on, tuning performance. And that's great. But there's a much easier way. And that's how to fix things with math rather than with engineering, right? So you basically go and distill. So AutoGluon, what we basically do is we take the models that come out of AutoGluon, and then we train a simpler model that matches the AutoGluon output. And so then, you have a good result. The problem is you need to generate good synthetic data via sampler to have a larger data set for distillation. So the first thing that you could do for distillation, you could just say, well, I want my function f, which is the teacher, and the student g, I want them to be close. Because if they're really close, then, well, the student and teacher perform the same and everything's great. The problem is you cannot do this because, one is this Rube-Goldberg contraption of many different systems, and the other one is, let's say, a deep network or, gradient boosted tree. So as people have realized in distillation, well, uniform convergence is too stringent, so you want to actually replace this with a weighted distance and an appropriate loss function. So you have some loss function between f and g, and then you weigh it over the training data. The problem is, though, we only have a small amount of empirical data, namely the training set. Especially for tabular data, that's a very common thing. And so, okay, fine, so you replace it with an empirical average, but this is only as good as the data that we can use for distillation. So think of it this way. You start off with the original data set. You have some, covariates and labels. You then get the, AutoML generated model, which gives you another set of labels for the same data. And then you want to move this over to a distilled model. But if the data set is quite small, then, well, you pay basically the statistical penalty twice, namely once to perform, empirical regularized risk minimization, and then you perform, again, empirical risk minimization between the teacher and the student. And the problem is basically, you have this VC dimension minus log delta, which is, the probability divided by m square root. So this is a standard VC type bound, and you can design 20 other bounds, which will tell you something qualitatively very similar. Namely, if you don't have a lot of data, you're screwed. So we need a larger data set for distillation. And so what we did is we performed some dataset synthesis. So you essentially sample from a surrogate distribution Q. And now what you do is you pay the price for solving the wrong problem. So you introduce a bit of bias, but you drastically drive down the variance because now that M is much larger. But then you have to pay a penalty for, that bias, namely the distance between the two distributions. And rather than that one, you can use, the Cox-Marklavka inequality and other ways to basically, for instance, take an arbitrary integral probability metric to measure the distance between P and Q. But by and large, you get this expression where now it's how well can I solve the bias problem, the variance bound for that bias problem, which is much better, and then you have a last term which essentially measures that bias. Now, when you generate data, usually when you perform density estimation and synthetic data generation, you would go and generate this data from scratch. But you don't really need to do that. What you can basically do is you can steal an idea from contrastive divergence, namely to start sampling off the true distribution, which we have. We just perform one Gibbs sample pass. And then you just, in order to estimate those P of xi's given everything but that coordinate, well, you just use a transformer. So does it work? Well, actually it does. And if you look at the picture here, you'll see that, well, you get something that's between 1 and 4 orders of magnitude faster, depending on the model and the choices and relative to what compared to. So H2O is pretty competitive. And basically what you see is that if you pick the best out of, 4 different models, rather than, just the deep network or the light GBM or whatever, you get something that loses essentially nothing relative to the full accuracy, but is, 4 orders of magnitude faster. So this is accelerating your code with math rather than with a lot of blood, sweat, and engineering. If you want to pick a specific model, well, okay, you can pick a neural network and they still work quite well, except that, well, you lose a bit of accuracy, but now you can just run this in, your preferred TVM, TensorRT, or whatever inference system that you want. Okay. So to conclude, I believe that the almost single-minded quest for hyperparameter optimization is a little bit overhyped. And if you combine many models, maybe mediocre ones, you can often get a better outcome than, finding that one single best model. Bagging is good, stacking is even better. And if you then want to get something that's fast, well, you distill. Now, this gives you a one-stop shop for better models. You don't really need any experience, but of course, if you know what to do, you can improve. So it's an open source project. We wholeheartedly invite you to join us and to help us with this. There are 2 papers on arXiv. Search for Nick Erickson and you'll find the papers. With that, thanks a lot and see you maybe next year in person.